right, so last time we talked about exactly what temperature and heat are. Temperature being the speed of the molecules inside a substance, and then heat being the transfer of that energy to something else. So given those two definitions of temperature and heat, now we can start thinking about just how fast these substances will change when they're exposed to incoming energy. So the question becomes, or a question that we could ask that might motivate this, is how do you know how much time is needed for a thermometer to be in thermal equilibrium with the object it's measuring? Okay, so if we have some object A and we put a little thermometer on it, thermometer is not going to be instantaneously the same temperature, right? So some amount of time has to pass, right? While these two things get to thermal equilibrium. So the question is, what dictates that? What determines how fast or how slow, or how much energy is exchanged when this happens? So before we talk about the time aspect, let's just talk about how much we expect it to change. So different substances have different capacities for storing internal energy. And you all know this. If you have a spoon or something with a wooden handle, you can sometimes leave that like on the stove when you're cooking and it doesn't get hot. But if you have a spoon, a large like cooking spoon with a metal handle, where the whole thing is metal, you have to be more careful with those because they actually get hot if you leave them in the wrong spot. If you've ever put anything in a microwave that has like a fluid or jelly inside, like a slice of apple pie, you can take it out and you'll notice that the sometimes the inside stuff is actually way hotter than the outside. Um, just like with this apple pie in the picture, sometimes the inside may be way too hot to eat, but you can still touch the crust. So clearly, different materials absorb heat in different ways. Okay, we need to figure out what is the thing about those materials that causes this. So, if since this is the case, different materials require different quantities of heat uh, to raise the temperature of that thing by a specific number of degrees. So, if we have object A here, and we want to raise its temperature by, I don't know, 2 degrees Celsius, and we have object B over here. If these two things are different substances, if these two things are like, I don't know, wood and metal or something like that, if these two things are different, we might have to add a lot of energy. I don't know, it could be we add 100 joules to object A to raise it 2 degrees, but object B only needs 10 joules of energy. So there's something about these different materials and their properties that actually causes energy to go much further in one case versus another. And it is important to remember that this incoming energy is spread out through all sorts of different kinds of molecular interactions, molecular energies. So if you have incoming energy, you're going to get some going to translational motion, rotational motion, and vibrational motion. So that's where all of this energy is going into. Now we can actually define this feature of objects. So the specific heat capacity of any substance. This is a little tricky. This specific heat capacity is defined as the quantity of heat required to change the temperature. Okay. So Q for quantity, to change the temperature, delta T, of a unit mass of a substance by 1 degree Celsius. Okay. So essentially all that is saying is if we have like a 1 kilogram or 1 gram mass, we're going to talk about this in terms of grams since we're going to be doing smaller things like water in a cup. You'd want to talk about that in grams, not kilograms. Okay, so if we have a unit mass here, oops, 1G, okay, and we want to increase this temperature by 1 degree Celsius. Okay, the definition of specific heat capacity, whatever this substance is, when we have this setup of this substance, how much ever heat we need to put in, that's the specific heat capacity. Okay, so you can think about this calculation as simply like the most basic calculation you can do. Okay, most basic. So it's essentially like how to get the smallest amount of the substance to change by 1 degree. That's going to be your specific heat capacity. Or we can represent this with an equation. So if we know the specific heat capacity of a substance, and there's tables out there online, you can look up almost anything in. If we know this specific heat capacity, which is C, then we can actually calculate this quantity of heat as transferred in or out when some mass undergoes a change in temperature delta T. And here's our equation to calculate that. So the whole idea here is we could think of specific heat capacity as thermal inertia. So if there's a big C value, that means it really wants to stay the same temperature. You have to put in a lot of energy to make it change. If it has a little specific heat capacity, just putting in a little bit of energy is going to cause a big temperature change. Um, yeah. And then to better understand this, you can think about it as like a linear equation. Okay. So we have this Q equals MC delta T. Oops, sorry. I'll fix that. So if you look at this online or you're doing some extra studying with other resources, you'll probably see this as Q equals MC delta T. I think the book actually does CM delta T. But I have it here as Q equals MC delta T in my slides, so I'll leave it. It's fine. So if we have Q equals MC delta T, we could actually think about this as Y equals MX. And we're going to assume B is 0, right? Our Y-intercept. So we won't worry about that. So remember how the whole linear equation goes? Linear equation, if you put in an X, you get out a Y. So the whole idea here is if you put in a change in temperature, you're going to get out some value of heat exchange. Anytime that temperature changes of a substance, that's going to correspond to some heat exchange, which means our M, our slope, is actually determined by the mass and is determined by the specific heat capacity. So if you have a large specific heat capacity, you're going to have a big slope. A small specific heat capacity, it's going to be a smaller slope. So the mass and the specific heat capacity dictate how the temperature is going to change here and how much energy needs to be input to make this change. Okay, let's just look at a quick example. So how much energy is required to raise the temperature of 100 grams of water by 2 degrees Celsius? All right. Well, we know what the specific heat of water is. We can look that up. We know we have 100 grams of this, and we're trying to raise this temperature by 2 degrees Celsius. So we have all the components we need. So just for thoroughness, you could say here's our tub of 100 grams of water. And we know we want to add 2 degrees Celsius to it. Okay. Now we know how much thermal inertia this water has, right? We know that's C. So the question is, how much heat do we need to add to this to make this happen? So we can just plug in everything we know. We've got C, we've got the mass of the water, and we have temperature. Now notice what happens here with the units. So the units on the specific heat is joule per gram Celsius, right? So the units work out here. I know there's a lot of stuff going on in the units, but if you notice, you've got a per mass in there, right? So that means when we multiply by the mass, the g's cancel. We also have this dependence in the specific heat. We've got a C in there for Celsius, so it depends on temperature. So that C is going to cancel out. And what's left over is just joules, just that amount of input energy we need. Okay. So to answer the question, to raise this temperature of 100 grams of water by 2 degrees Celsius, we need 838 joules of energy input into this cube of water. Now, the specific heat of water is very useful because the specific heat of water is actually pretty big. That, what, 4.19? Yeah. That's actually a fairly large number when you compare it to other materials. So that's why you see water being used as a heat sink in so many cases. So you've got these hydrogen bonds, right? And some of you that have taken chemistry will hopefully remember this. But you have these actually really strong hydrogen bonds, and that's actually what causes a lot of this thermal inertia or this really high specific heat. And then you can see water being used, especially in like car engines. A lot of times people will use like antifreeze or something like that, so it doesn't freeze in the winter. But if you live in like a tropical area where you don't have to worry about freezing, you could actually just put water in your car. And that will actually work as an engine coolant. And then, of course, for like the gamers among us, you can actually make a liquid cooled PC. So the whole idea is you can run water through the components that are hot. That water will absorb a lot of that heat, and then you push that water on so you can remove that heat and move it elsewhere. So this whole idea that just having this really high heat capacity makes water a useful tool when you're trying to keep things cool or move heat around. We can actually see this in nature. So the whole idea that water has a large thermal inertia, you can see this in the Atlantic because the Gulf Stream, which I've labeled here, the Gulf Stream actually carries this warmer water up to the northeast from the Caribbean. And it actually will keep a lot of its heat as it gets to the coast of Europe. So what happens is along the coast of Europe, you actually get some warmth, even though, if you think about it, a lot of cities in Europe, latitudinally, because this is your latitude, latitudinally, they're like even with Canada, and Canada's really cold, but because they have this like nice warm ocean breeze that comes up from the Caribbean and the Gulf Stream, it keeps them a little warmer. You can actually see a similar effect here in the US. For anybody that's ever been to the West Coast, especially Southern California or San Francisco. So, usually um, here in North America, the winds across North America in this band of latitude is usually westerly, so from the west. So the whole idea here is that on the west coast, air moves from the Pacific Ocean to land. Okay, I've labeled it here. And when this happens, the water is warmer than the air in the winter and cooler than the air in the summer. Um, so in the wintertime, the water warms the air that moves over it. Okay, and this is actually going to warm the coastal region. But then in the summertime, the water actually cools the air. The water is going to be cooler than the air. So actually, when you get this warm air on the west coast in the summertime, it's going to that he's going to go into the ocean. So you're actually going to get a net cooling effect. Okay, and this is going to cool the coastal regions. So it turns out, especially in San Francisco, if you've been there at different times of the year, San Francisco stays a pretty consistent temperature year round, just for this reason, because it gets cooling in the summertime because of this specific heat capacity of the ocean. Then it gets heating in the wintertime because of the specific heat capacity of the ocean. Uh, this is actually a picture I took myself when I was at a conference in San Francisco. You can see barely that a lot of the trees are actually, they still have leaves on them, and this conference was actually in December. So you can see that San Fran actually stays a pretty consistent temperature. Um, okay, so we've talked about so far, even from last lecture, we've talked about temperature, how it's the measure of kinetic energy of molecules. We talked about heat, which is the transfer of energy, um, energy in motion. Now we've just talked about um, how things will, or how effectively things will absorb or release energy, because that's the specific heat. Now, the last thing we need to talk about in this lecture is when things absorb or release energy, what happens to them? Okay, and this comes along in the idea of thermal expansion. So when the temperature of a substance is increased, its molecules or atoms jiggle faster and they move further apart. Okay, now when these molecules actually jiggle and move apart, you get this expansion, right? If there's more motion in all of the molecules, the thing has to get a little bit bigger. This is true for almost everything. There are very few really weird exceptions, but this is a general rule of thumb. Heat will increase the volume, make the thing bigger. Cold will make it contract and decrease the volume. And this is true for all forms of matter, solids, liquids, gases, and plasmas. Generally expand when they are heated and they contract when they are cooled. This expansion of substances must be accommodated in structures and devices. So you can see here, you've got this thermal expansion joint in, I believe, what is a bridge. So it's got to be able to flex when things start expanding and contracting. You can also see here on this bridge, there we go. You've got like this sawtooth type pattern. And what happens is when the bridge expands or contracts, there's enough teeth here to sort of keep the road together that you can drive over, even though the bridge is getting shorter, or on a hot day, it's going to sort of push together. So you need that flexibility. And there's several joints like this across any given bridge. Um, Actually, what's really neat is the Golden Gate Bridge here in San Francisco. Another picture I took myself. The Golden Gate Bridge actually contracts more than a meter. That's 3.28 feet in cold weather. So in San Fran on the coldest days, you're going to get a bridge that shrinks by over a yard. Um, it doesn't happen just at one point, so you can't like see it happen. But if you think about, just a little bit of contraction at all of these joints along the way, if you add up all those contractions, you'll actually get over a foot or over a yard. So this is something important to think about. Even like your phone. If you talk on your phone for a long time, battery starts heating up. The designers and engineers of these phones have to take that thermal expansion into account. So, the battery doesn't swell and burst through your phone or something. Um, Now we can revisit the thermometer that we talked about last lecture. We could ask the question, well, if you heat up a thermometer and the mercury gets bigger, right? The mercury expands, wouldn't the glass also expand? So your markings on your thermometer, are they not also going to get bigger as the glass expands? Yes, they will. But you got to remember that mercury and glass have two very different specific heats. So mercury has a really small specific heat, 0.14 joules per gram Celsius. Glass is much higher. It's 0.753. So that means the mercury is going to expand and contract so much more than the glass. So this could be more change due to changes in temperature. So that's why when you make a thermometer, you need to be really mindful of the materials that you're using, right? You want something that changes a lot with a small specific heat, but you want to put that inside something that doesn't change at all or changes very little. You can also use this idea of expansion and contraction in bimetallic strips. And these, if you've ever like seen the cover of a thermostat come off, you've seen these before. Um, so these bimetallic strips essentially just have two different types of metal, one on the upper side, the one on the lower side, like this brass and iron strip here. The idea is because these two metals have different specific heats, you can make this thing like bend and contract given whatever temperature you're putting it in. So heating the iron side will cause the curve downward. At room temperature, both of these should be nice and level since they're the same temperature and it's not an extreme temperature. And then, of course, you could make like the brass contract if you put ice on it, and that will bend this bimetallic strip up. So the whole idea is that with a bimetallic strip like this one here, if you put this in a thermostat that controls your furnace, if it gets too cold, what's going to happen is it's going to shrink down. And that's what the spiral is for. The spiral gets you a lot of the material in there, so there's a lot of shrinkage. Um, when this thing shrinks, it's going to come off of this switch here, the little white part, right? Because this thing's going to get smaller. And then when it breaks that circuit, that's the sensor is like, oh, the circuit's broken. We need to turn the furnace on. And then the house gets warm again, right? So when the furnace turns on, the house gets warm. This thing will expand again. This is about to be a really cluttered picture, but this thing will expand again and then touch the circuit. And then when the circuit is complete again, when these two things touch, that means the furnace turns off. Wow, I can't write. There we go. Okay, let's see. Let me skip ahead. Perfect. Okay. The last thing I want to talk about really quick is just the expansion of water. So water expands when it's heated, right? Just like everything else. But what's really creepy is it does not expand in this really small temperature range from 0 degrees Celsius to 4 degrees Celsius. Remember, this is the freezing point of water here. That's where ice starts to form. So from ice up to still really cold, but 4 degrees Celsius. In this range, even though the water's being heated, it doesn't expand. That's because ice has this crystalline structure with open structured crystals. So we've got liquid water here. But when you freeze it, when you get to this 0 degrees Celsius, these hydrogen atoms actually make this nice, pretty crystal lattice structure. Okay. Now notice what happens. There's so much empty space here, right? To make this crystalline structure, all these hydrogen molecules, they have to spread out to make this. You can see the difference here. So when they make this structure, they spread out and it actually causes an increase in volume. Right? They take up more space. So the water molecules in this structure, when they do this, that makes ice less dense, right? There's an increase in volume, but same amount of stuff. So this is why ice floats. It bloats itself, right? And then that's what allows it to float on top of the more dense water. Um, so the whole reason that ice doesn't actually expand in this range, the 0 degrees Celsius to 4 degrees Celsius, is essentially when you start with ice and you start heating it up, there's still going to be some of those crystals left over. So you sort of get this slush. Okay. Um, these crystals do, like I said on the last slide, it bloats the water, okay, causes a slight increase in volume. But um, what happens is you've got this as you're increasing the temperature of the water, not all of these microscopic crystals melt, right? Because here at 0, you've got crystals. But then they don't all melt at once. It's not instantaneous. So you get all these little crystals still floating around. They're still like large. They have a big volume, right? Because they're those crystal structures. So essentially, you've got this microscopic slush, it continues to melt in the water. The volume decreases while the temperature increases, right? Because you're still melting these crystals. So what you're seeing here, or let me rephrase that, what you would expect to see is from 0 to 4 degrees, you would expect to see that increase instantly, right? You're heating it, it should expand, but what you actually see, don't switch colors, what you actually see is this short little decrease first, and then it starts to increase. So this little weirdness here, weird, that really is just due to not melting all the ice at once and having these little crystals that have a nice form to them, a big voluminous form. Those are floating around in there, which gives water some really weird properties. The reason this is important is because this range, this 0 degree water up to 4 degree water, it's less dense than uh, warmer water. And we can see that on this plot, right? This is getting crowded, but we're going to do it. We're going to power through. So here's our volume, right? So on either side, here and here, you can see that there's a slight increase in volume. Okay, so that means the slush over here is going to be a little less dense than water above 4 degrees C. Well, that means if it's less dense, it's going to float above the warmer water. And we can see this in this picture here. So the whole idea is we have regular water down here. Then we get this water and slush with the crystals. Ooh, I did not write that well. Let's try that again. So this is a mix of mostly water, some crystals. This is less dense than the warmer water, so it's going to float above the warmer water. And then above that, of course, we have the ice. This is full of crystals. It's all crystals. So that is the least dense, and it will rise straight to the top. So this is the whole reason why if you go to a very deep lake, and this isn't going to work in like 3 feet of water, but if you go to a very deep lake, the bottom of these lakes usually stay at 4 degrees year round, just because that's sort of your threshold where the water is just warm enough to where there's no crystals, so it's going to sink to the bottom. It's the most dense, and then there's no really sunlight making it in from the top, so it never gets heated up. And then so you can go to most of the Great Lakes, I think, at least at the deeper ones. And if you go to the bottom, you're going to be at 4 degrees C. This is why fish tend to just drop down to the bottom during the wintertime, because they don't have to worry about the slush, they don't have to worry about the ice, and they can hang out and actually survive the winter. So the next topic we'll talk about, next lecture, is actually heat transfer. So we've talked about temperature, we've talked about the transfer of that energy through heat. We talked about the properties of matter that cause them to absorb or emit heat, and what that looks like. But we haven't talked about the transfer itself, like how does heat go from one object to another? And that'll be the topic for the next lecture. So until then, if you have any questions, please let me know.